All right, welcome to The Explainer. Today, we're going to go on a pretty incredible high-speed journey. We're going to follow just one single piece of data from the moment you click send to the second it arrives at its destination.
I mean, it feels instant, right? But in that blink of an eye, there's this amazing, highly organized trip taking place. So let's do it. Let's follow a single data packet and see its incredible journey across the wild world of the internet.
So where does it all kick off? Well, it starts right here, with you. The moment you make a request, like loading a web page, you create the spark. And this all begins right there on your own local network. Which begs the question, what even is a network? You know, at its core, it's really just a group of devices. Could be 2 billion, that have all agreed to talk to each other using a common set of rules. This one simple idea is the foundation for, well, everything.
Our tiny data packet has just been born inside a local area network, or LAN. The easiest way to think of this is as its local neighborhood, your home, your office. But its destination is way, way out there, on the wide area network, the WAN, which is basically just countless neighborhoods all connected together to form the internet.
Okay, so before our packet can even think about leaving its neighborhood, it needs some ID. Kind of like a passport, right? It has to know exactly where it came from and where it's going. And for that, it needs 2 absolutely crucial digital addresses.
First up is the MAC address. Think of this as your device's permanent, unchangeable fingerprint. It's literally burned into the network hardware by the manufacturer. Now you'll see on the slide it says Layer 2. Don't worry about that just yet. We're going to put that all together in a bit. For now, just remember, MAC address is the hardware's permanent ID.
The second piece of ID is the IP address. So if the MAC address is that permanent fingerprint, the IP address is more like a temporary mailing address. It tells the global internet where to send the mail today. And again, you'll see Layer 3 mentioned. We'll see where that fits into the big picture really soon.
And this brings us to a really key distinction. Inside your home, on your LAN, every single one of your devices, your phone, your laptop, your smart TV, it gets its own private IP address. But when any of those devices talk to the outside world, they all share one single public IP address, which belongs to your router.
So how do all your devices share one public address without getting their mail mixed up? Well, the magic behind that is called Network Address Translation, or NAT. Your router basically acts like a digital post office, keeping this careful list of which internal device made which request. So when the replies come back, they get to the right computer or phone.
Now, just having an address isn't always enough, especially when you're dealing with huge, complex networks. To keep things running smoothly, these massive digital cities need to be organized into smaller districts. And for network professionals, especially folks like ethical hackers, understanding this is absolutely critical.
This is done through something called subnetting. It's really just like taking a giant, sprawling digital city and drawing lines on the map to create smaller, more organized neighborhoods. This makes traffic flow way more efficiently and just helps manage everything connected to it.
Okay, so our data packet now has its identity papers in order. But how is it actually going to travel? It needs a plan, and it has to make a pretty big choice between 2 very different options. Does our packet want speed, or does it want reliability? If it's part of a video stream or an online game, it'll probably use UDP. Think of that like sending a postcard. It's fast, it's efficient, but hey, there's no guarantee it'll arrive. But if it's part of an email or a web page, it's going to use TCP. That's like sending certified mail. It's a bit slower, yeah, but it guarantees every single piece arrives in the correct order. And for that reliable TCP connection to work, a polite little conversation has to happen first. It's called the 3-way handshake. Your computer sends a SYN packet to say hello. The server replies with a SYN ACK that says, yep, I'm here and I hear you. And finally, your computer sends an ACK to say, great, let's start talking. Only after this digital handshake is done can the actual data start flowing. Our packet has made it. It used its IP address to travel across the internet and arrived at the correct server. It's on the right city block. But now it needs to find the specific service it's looking for. It needs to find the right door. And that door is called a port. So if the IP address gets the data to the correct building, the port number gets it to the right apartment. It's just a logical endpoint that tells the server which specific program, like a web server or an email service, is supposed to get this packet. This is why different services have standard, well-known port numbers that they're always listening on. So for example, web traffic usually heads for port 80 or the secure port 443, while an email service waits for data to show up on port 25. Our packet finds its port and delivers its message.
You know, this entire journey we've been talking about, it wasn't random at all. In fact, it followed a very strict, standardized framework that governs all network communication. Think of it as the universal rulebook for the internet.
So we'll build this model from the top down, starting with layer 7, the application layer. This is the only part of the process you directly see and interact with. When you type a web address into your browser or hit send on an email, you are creating the data right here at the human interaction layer.
Okay, once your request is created, it's handed down the chain to layer 4, the transport layer. To get it ready for the journey, this layer breaks your big message into smaller, numbered chunks called segments. And this is where that crucial choice we talked about earlier is made. Will it be sent via the fast UDP or the reliable TCP?
Down at layer 3, the network layer, our little segments get their travel visas. The destination IP address is stamped on, officially turning each segment into the packet we've been following. This layer acts as the master navigator, using that IP address to calculate the best and fastest route across the entire internet.
And now for layer 2, the data link layer. This layer is focused only on the very next step of the journey. It wraps the packet in what's called a frame and adds the physical MAC address of the next device it needs to talk to, like your computer sending it to your home router.
And finally, we hit rock bottom, layer 1, the physical layer. At this point, all that beautifully organized information is converted into the raw language of machines, a stream of ones and zeros, sent as electrical pulses through a cable, flashes of light in a fiber optic line, or radio waves through the air.
From a simple click to a physical signal and back again, all in a millisecond. Understanding this incredible journey is really the first step to understanding how networks work and, more importantly, how to protect them.